First, I would like to say thank you for the organizers. So this is joint work with Professor Jack Cullen, Dr. Jonghyuk Park, and Jiorin Park. So the outline is I will give some introduction, and there is some motivations about strongly regular graph. Then I will introduce our main results and the tools we use for our proof. As we see, many people introduce graphs. So for this talk, the graphs are undirected and simple graphs. We say vertex x, y are adjacent if x, y is an edge, and a click in a graph is a set of parallel adjacent vertices of the graph, and a co-click is a graph. And a graph is a set of pairwise non-adjacent vertices. The adjacency matrix A of a graph is the matrix whose row and column are indexed by its vertices, in which its entry becomes 1 if xy is an edge, otherwise we have 0. So in this case, the eigenvalue of our graph are the eigenvalue of the adjacency matrix. Given a graph G, for each vertex x in the vertex set, we denote by G of x the set of vertices in G that are adjacent to x. We call them the neighbor of x. And a graph is called k-regular if every vertex in G has k neighbors. So a graph G is strongly regular with parameters n, k, lambda, mu. If it is k-regular and n vertices in which two adjacent vertices have lambda common neighbor, and any two pair of distinct non-adjacent vertices have mu common neighbors. Moreover, we say a strongly regular graph with at least two vertices is called primitive if both the graph and its complement are connected. In our talk, there are two more important families we use. The first one is take an orthogonal array with parameters Vm. This is a m times v square array. It is entries from 1 up to v, in which the v square pairs in any two distinct rows are all different. An orthogonal array V3 is closely related to the Latin scale. Now take an orthogonal array on Vm. Then when we take the vertex set of this as the column of A, when we say, sorry, take as vertex set the column of O, two columns are adjacent if they have the same interest in one position. Otherwise, they are non-adjacent. This gives a strongly regular graph with parameters v square. The k value becomes m times v minus 1. Lambda becomes v minus 2 plus m minus 1 times m minus 2. And mu becomes m times m minus 1. And the smallest eigenvalue for such graph is negative m. So we call this family Latin square family. Our second family is take a Steiner system S with point set and block set that is 2VM1 design, when P is the V element set point set and B is the family of M element subset of B. We call the block set in which two element subset of P is contained in exactly one block. So we will construct a graph as follows. The vertex set is the block set and two blocks are adjacent if they intersect in one point. This gives a strongly regular graph with parameters v times v minus 1 over m times m minus 1, and the k value becomes m times v minus m over m minus 1. Lambda becomes m minus 1 square plus v minus 1 over m minus 1 minus 2, and mu equals to m squared. And the smallest eigenvalue for this graph is negative m. And we call this family the Steiner family or block graph of Steiner system. The theme shows the following result. The strongly regular graph with integral smallest eigenvalue, negative m, when m at least 2r, the complete multipartite graph, the Latin square graph, the block graph of Steiner system, or some finite many further graphs. We can find this result in the new book by Brouwer and Van Baldegem. The numerator shows this result. It's a refinement of the previous result. Let m be at least 2, which is an integer. There exists a constant, capital N, dependent on m, which is positive, says that any primitive strongly regular graph with parameters nk lambda and smallest eigenvalue, negative m, satisfies either n is at most capital Nm or mu is m times m minus 1 or m squared. This means we have the graph, Latin square graph, or the block graph of Steiner system, or the order of the strongly regular graph is bounded by some constant. If we consider for M3, the largest open case of a set of feasible parameters of primitive strongly regular graph with smallest eigenvalue, negative 3 and mu different from 6 and 9 was on order 1911 with mu 27. Cullen and myself, we show that there is no strongly regular graph with their parameters. So the next case is with a graph on 1344 vertices. So we have the order at most 1344. So in this talk, we will roll out the following two infinite family of feasible parameters n, k, lambda, mu of strongly regular graph. We show that there does not exist strongly regular graph with parameters nk lambda mu for some positive integer t. When we have mu here in the first one, 2t plus 1, m t squared plus 1, lambda equals to 2t plus 1 times 32 t cubed plus 40 minus 1, and k equals to 2t times 40 plus 1 times mu. So the k value is dependent on mu, and the second one is also like that. The k value is dependent on mu. So we'll see how we prove this one. Note that 41 in the first part, we have the parameter of a vertex with smallest eigenvalue negative 3 on order of 1911. So let's see the tools we use for our proof. Cullen and Park show that let G be a strongly regular graph with parameters nk lambda mu. Let x be a vertex of G and let capital C bar be a co-clique of order C bar in G of x. Then C bar choose 2 times mu minus 1 is at least C bar times lambda plus 1 minus k. We call this one the claw bound. So based on this lemma, Graves, Cullen, and Park give a bound on the order of a clique in a strongly regular graph when the graph does not contain a clique of order C bar. The result is let G be a strongly regular graph with parameters nk lambda mu if C bar choose 2 times mu minus 1 is less than C bar times lambda plus 1 minus k for some integer C bar at least 2, then the graph contains a clique of order at least 2 plus 1 minus C bar minus 2 times mu minus 1. So we will use this idea later. Let G be a strongly regular graph with parameters nk lambda mu and smallest eigenvalue negative m. Let C be a clique of order C. Then we know C is at most 1 plus k over m. This inequality is called the Delsart bound. I think many of us are familiar with this one. First, I will show the result of Graves, Cullen, and Park, how they saw the new bound for the cliques if there are some restriction. Let HAT be the graph with 1 plus A plus T vertices consisting of a complete graph K on A plus T vertex and a vertex adjacent to exactly the A vertex of the complete graph on A plus T. Then Graves, Cullen, and Park gives the following lemma that gives the relationship between A, T, and M for a graph with smallest eigenvalue negative M and contains this H or H at AT. We call it hat. So let G be a graph with smallest eigenvalue negative M. Assume that the graph contains an induced hat, then A minus M times M minus 1 times T minus M minus 1 square is at most M times M minus 1 the whole square. We have this condition. So based on this lemma, they derived a method which restricts order of a maximal clique in a strongly regular graph. The result is as follows. Let G be a strongly regular graph with parameters nk lambda mu having smallest eigenvalue negative m. Let C be a maximum clique of G with order C if mu is at least m times m minus 1 and the order of the clique is at least mu square over mu minus m times m minus 1 minus m plus 1, then this equality is at least 0. We denote this polynomial on the left-hand side of the inequality by mg of c. And we have to take a note here that this left-hand side is cubic polynomial in the variable c, and its leading coefficient is positive. So if we have if we put the value of c with the Delsart bound 1 plus k over m, and if we get the negative, I mean if we get contradiction in this lemma, then we can improve the Delsart bound. And this is a big result of their paper. So here we give, sorry, I have to say more here. Using this idea, they just show the non-existence of some infinite family of strongly regular graphs. Then we can extend this result also. Let G be a strongly regular graph with parameters nk lambda mu and smallest eigenvalue negative m at just at most negative 2 and mu is greater than 4m times m minus 1. Assume that there are two distinct maximal cliques C1 and C2 in which their order is at least mu plus m minus 1 and the number of vertices, the common number of vertices in the two cliques are at least 5 mu plus 3 times m minus 1 minus under root of mu minus 3 m minus 1 the whole square minus 24 m minus 1 square over 6. Then the order of the intersection of the two cliques is equals to mu, and each of the cliques have order mu plus m minus 1. So if we have some graphs that satisfy this condition, then we can extend the result by Grave, Cullen, and Park. So here I will give sketch of a proof for the graphs we say. In this part, I will give a rough sketch of the proof how one can show that there is no strongly graph G with parameters nk lambda mu for this case, for the first part. When here 20 is equals to 1, it's already known. So note that the smallest eigenvalue of this graph is negative t to t minus 1. So if you have a graph with these parameters, using the cubic polynomial by Grave, Cullen, and Park, we can show that the maximum clique has order at most 16 t cubed plus 12 t squared plus t plus 1. And moreover, it's not difficult to find a clique of order mu plus m minus 1 equals to 16 t cubed plus 8 squared plus 40 plus 1 in G. We have to use the fact that the neighbor of any vertex x in G must contain a co-clique of order at most 14. So by considering the non-existence of a co-clique on 40 minus plus 1 vertices, then we can show the existence of a clique with this order. Next, as this inequality is true, now we can easily find two distinct cliques, C1 and C2, with order of C1 equals to C2 equals 16 t cubed plus 8 t squared plus 40 plus 1 that intersect in at least 16 t cubed plus 4 t squared minus ct, 3t minus 4 vertices. Here, first we already find two cliques with this order. Then to show the number of intersection, we have to count the number of vertices between, and we use the smallest eigenvalue and also the equitable partition, so we can find this case. So as the number of vertices, the common number of vertices in these two cliques is greater than the number, an inequality in the lemma about the maximal cliques, this satisfies that lemma. So we have that C1 and theta are both maximal with order 16 t cubed plus m 8 t squared plus 40 plus 1, and they intersect in exactly mu vertices. Then after that, we can show that this is not possible. First, we have to show we don't have quadrangle in the graph which contains these two cliques. After that, it's easy to show this case not exist. Okay, I will give some open problem. There exist many strongly regular graphs with a parameter for n equals to 276. We can find this in this book. On this moment, there are 12 feasible parameter set of primitive, strongly regular graphs with parameters with smallest eigenvalue -3 and greater than 276, and mu's different from 6 and 9, which are still open. To say the graph on 276 is also have smallest eigenvalue -3, then we believe that n of 3 must be 276. So we give this conjecture. Let G be a primitive strongly regular graph with parameters nk, lambda mu, and smallest eigenvalue -3. Then either mu is 6 or 9, or n is at most 276. Here, the construction of the graph on 176 is from the graph with order in 275, and the 12 graphs, remaining 12 unknown open cases they have mu big, so we just say we believe it may be true. Okay, thank you. This all.
Okay, thank you. Thank you very much for your talk. Any questions to Michael? Well, if not, then let us thank again Michael for this interesting talk with finishing up to open problems and even some conjectures. So every time it is very nice to have some open problems to continue research. Thank you very much. Thank you.